So today, we are talking about LoRa and QLoRA. So it's like the low rank fine-tuning, representation fine-tuning of the LLMs. Before I jump into the details of LoRa and the QLoRA, I want to first briefly touch on the pre-training and fine-tuning training framework of the LLM. Right? So if you know about like how to actually train a LLM, so usually they fall into two stages. The first stage is the pre-training phase, where you can leverage lots of unlabeled text and just do, for example, the next token prediction, right? This is more to ground the model to understand the grammars, the basic reasonings, and get the model prepared for the language understanding task. And then the second stage is fine tuning. So fine tuning is that you can further fine tune the parameters of the models and for specific tasks. It can be for Q&As, like question answering. It can be for name entity recognition, sentiment predictions, document classifications, all different types of downstream tasks. So this is how usually like the LM is trained, and then we further instruction fine tune it to specific downstream task. If you compare the pre-training and the fine tuning, so the high level, I will think the algorithm is all. Generally speaking, it can be all framed as like just the next token prediction, especially for the GPT model, right? So lots of current chatbot, ChatGPT, open source or closed source LLM today is a GPT-based model, so it's always like generate the next token given your input. So basically, the loss is always how we can best generate the next token predicted. The data for the pre-training usually is the raw data. It can be very, very large, like can be containing trillions of words, but it may be lower quality, but it comes in large quantity. But people have also found that if we are able to do certain pre-processing or do the quality checks of this pre-trained data set, it usually leads to better performance. So not quality may not necessarily be true, but if there's any bandwidth or any the technology has been developed to clean up and improve the quality of the pre-training data sets also. On the fine-tuning side, is more of a carefully curated text, usually comes into a pair of prompt and response. This usually comes in low quantity because you need kind of these pairs of instruction and response, kind of like a label data set. But usually the high is kind of guarantees a high quality for the model training. In terms of the computing resource, pre-training usually requires lots of days of GPU to train the kind of foundational model like the GPT model, Llama model, Palm model, all the foundational models, pre-trained foundational models. Usually this takes the longest time and takes the most machines. And for the supervised fine-tuning, usually like it's a lot fewer days of training. Because the data set is a lot smaller, so the training time is also lots shorter to get the fine-tuned model. In today's talk, so that's a background for pre-training and fine-tuning. Today's meetup, we mainly focus on the fine-tuning session. And we specifically focus on one very important branch under fine-tuning, which is parameter-efficient fine-tuning. So the goal of this parameter efficient fine tuning is because the LLM has like really large sets of parameters, we want to find the methods that can allow us just to fine tune a small subset of the model parameters and yet to match the performance if we were to fine tune the full parameters of the models. So the key idea over here is, for example, you have like this is you have like a different task. For example, for the sentiment, question answering, a speech model, And then usually like the fine tuning is like you just get a pre-trained model and then you just fine tune, say without this, you just fine tune all parameters of the LLMs for that specific task, which in the end you may get like different copies of the LLMs for different tasks. Which may needs to like storage, additional storage, and also the loading in like really large models in and out. It's also takes long time. In this world of parameter efficient fine tuning is that all these tasks is going to share a one base LM, and then we are just going to learn the adapter weights for that specific task, right? So this one pre-trained LM is shared across all the tasks, and then we can adapt a subsets of this LM, of the LM, the weights, for the corresponding task. For example, we can have a PEFT. So this is parameter efficient fine tuning PEFT. We can have a set of PEFT weights for that adapted for sentiment analysis. Another PEFT module weights for QAs and another PEFT. So basically at the inference time, this will be always in your system. And depending on the task, you can just swap in and out a very small module, the pathways, combined with the pre-trained model there for the corresponding task over there. So and this is the additional storage. So you don't need to keep like multiple copies of this really big LM, different LLMs basically in the storage, but instead you can just keep one copy of the big model LLM, and then you can store just a very small sets of these adapter weights for different tasks. PEFT overview. So these are just general frameworks of what are the algorithms in PEFT. So there's this additive PEFT. So additive is like, so this gray part is the regional LM. So you can think of it as a regional LM, like using the regional transformer blocker, right? Additive is you are just going to add additional layers into your transformer blocks. We can show an example later. So this is basically you add additional layers to your LLM so that you are just going to train that additional layers to adapt to the new task. So the pink ones are all learnable, trainable parameters. So in the training phase, the original LLM parameters are going to be frozen, and then only the new added layers are going to be updated for the new task. So this is additive. There's also selective paths. Selective path, you can think of it as some layers of the transformer blocks are frozen and some layers of it are trainable. Usually people just freeze the lower layers of the weights, and then they're just going to fine tune the higher layers, like the top layers of the LM for the corresponding task, kind of to learn a higher representation, like just adapt the final layer, the top a few layers for the target task. Well, the reparameterization path, that's what we were talking about today, is the LoRA type of approach. It's going to, similar to the additive, it's going to have like a new module parallel to the original weight, and it's going to update this a few new parameters, and then it's going to add it back, like make just directly apply this additional nuances and changes to the original parameters. So basically, this part is going to be merged into the original LLM parameters. So in the end, you are still going to have the exact same architecture, no additional layer added. It's going to just to be the same LLM architecture, but with the parameters updated from this merge. So this is the like many different ways of how we can reduce the number of parameters during the fine tuning for a specific task. So for the adjective, so very common name there is adapters, but I think right now people just call adapters for all the PEFT methods. They just call it as adapters. But this is how the first adapters comes into place. Is this adjective belongs to the additive branch. So they are just going to add this adapter layer, right? Just as I mentioned, they were going to change the architecture by adding additional layers into the transformer block so that all these attention layers, feedforward layers are kept frozen. And during your fine tuning, you are just going to fine tune the adapter layers in your transformer blocks. And if you look into the adapter layers, it's going to be looking like kind of like an auto regressor, kind of auto encoder type of structure. Is this they first like a down projected into a smaller vector into a lower dimensional representation, and then they up projected to the original dimension. So this is kind of just doing some compression first, and then reconstruct the signals back to the original dimension. So this is how the adapter layer looks like. I think they designed it in such a way because first they want to minimize the number of parameters that they want to train, right? So with this shape, basically you can reduce, you can kind of doing some dimension reduction here, and so that you can reduce the number of parameters in your fine-tuning process. And also people may find the lower dimensional representation can help with the overfitting, right? And you don't need that many parameters to really adapt to a new task and prevent it from overfitting. So that's an example of adapters. And then let's move to the main role of today is the LoRa. So why I talk about adapter first, because in all the LoRa, so LoRa is proposed after adapters. So all the results that you see in the LoRa paper are compared to the fully fine-tuned model. Like basically you're going to fine-tune every parameters of the original model, which is really huge, right? And then they're also going to compare the performance to this adapter approach to see, okay, whether LoRa is a more effective PEFT method comparing to adapters. So the LoRa approach, again, to that difference question is you see the plus here. So the plus is like how they merge the deltas to the original pre-trained weights. So this is your pre-trained weights of the LLM. Like during the fine-tuning phase, this part is going to be kept frozen. It's not going to change. But in this, I think it follows kind of a similar structure to the adapters we see, right? So it's still this down project doing the dimension reduction first and then up, but it's doing it a different way. It's just doing it by matrix multiplication. So basically, it's like this is your original matrix, and then you are just going to do a delta matrix to apply to be added to the original weight matrix. And this delta matrix can be approximated, just can be calculated by two matrices like B and A. Well, the B and A, you kind of can doing some dimension reduction over there, right? So the A, say the A dimension is D by R, and the B dimension is R by D, and then multiply it together, you get D by D matrix. But if with the R, you kind of also doing some kind of dimension reduction and to compress the information into a more dense matrix of A and B, which is a D by R dimensions. So during the fine tuning time, they are just going to update the low rank matrix over here, and then they can just multiply this matrix and then sum it back to the pre-trained weights. And people see that usually it leads to like 10K less trainable parameters, which will correspond to needing to like 10K less training time, fine-tuning time. So which is like greatly shorten the time to fine-tune the LLM. And also it will require usually like three plus less GPU memories during the fine tuning. And it can apply to any linear layer, which means that it can apply to the query matrices, the value matrices, right? So if you know the transformer block, there's like a query matrices, key matrices, value matrices, etc., right? So this logic can be applied to all those matrices as long as it's a linear matrix over there. And also there's no inference overhead, which means that there's no architecture change, right? So once it merged back like plus, once this plus is complete, the inference time is exactly the same as the original LLM model. Not like the adapter approach where you add the additional layers, the inference time may increase because the information is just going to pass through more layers. Well, over here, it's exactly the same architecture, so there's no difference on the inference. Yeah, that's LoRA, general idea about LoRA. So the key advantages of LoRA is first, it can build many small LoRA modules for different tasks, right? So for different tasks, you can just keep a copy of A and B, and then at inference time, you can just merge it with the original pre-trained weights for the corresponding task. So you can basically keep a different copies of LoRA modules. Those are A and B matrices for different tasks. And also it makes training more efficient, memory also more efficient, and also it introduces no additional inference latencies to comparing to the original LM, the fully fine-tuned model. Official formulations for LoRA, which seems like straightforward, is the so this is your target is always the next token prediction, right? So this is kind of your context input, and this is all the sequence you generated before time t, and then you want to predict the next token. And then this is your pre-trained weights, and this delta phi is your B and A. So basically, right now the delta phi is a multiplication of B and A. And then this theta is the fine-tunable parameters, which is just the parameters in the matrix B and A, right? And this one is going to be only this deltas is going to be task specific incremental changes that you want to apply to the regional weights. And usually this theta fine-tunable parameters here will be a lot less, usually like a 10K fewer comparing to the original LLM parameters size. And then let's look at some of the results. So that's why I want to sort out some concept here first, including the FT. So whenever you see a FT, it's a fully fine-tuned model, which means that you just fine-tune all the parameters of the pre-trained model there, right? So ideally, we want this LoRa fine-tuning match or even better than the performance of the fully fine-tuned model. And they also compare it across different PEFT methods, like the BitFit, well, they only train the Bayes factors, kind of plus. So they're just going to train the Bayes in the linear term while freezing everyone else. And also this like pre-embedding and pre-layers is kind of they apply some additional prefixes to your input tokens or to the selected layers. I haven't disclosed like too much details over here, but if this is of interest to you, you can also look that. I think it's also a very interesting idea about how they what are the different strategies that they can incorporate additional learnable parameters into the LM. And also this adapter fine-tuning is exactly what I have mentioned, is this adding this additional adapter layers to the architecture in the transformer block. And then this adapter just be kept there throughout the training and inference. And also in this adapter tuning, there are many variants of adapters. So if you see the results, they compare it to adapter H, adapter L, P, and D. So the H is original design. So basically it's this design over here. I think the L and P, I think they made some modifications of where they want to add the adapter layers. So the original one is adapter will be added after the feed forward layers. And I think L may also add it kind of after the layer norm. So P is another variant of L. Adapter D is kind of they apply some drop-offs to the adapter layers. So basically, if you see like adapter H, LPD, it's just all the different tricks that they look for the variance of adapters regarding to where they want to put the adapters at what after or before what layers, and also whether the dropout is applied to the adapter layers. And then let's look at some results. So here they use one model. So basically it's like one model with a different size. So you see this is a robust BERT. So it's kind of just an encoder model. So encoder model, so basically these PEFT methods can apply to any transformer block, which means that it can applies to both encoder models and decoder models. So this paper first evaluated on the encoder models, right? So an encoder model is the robust BERT. And then they have the base size, large size, and extra large size. And then this is the different strategies of how they want to fine tune the model. So you see, I think you should familiar with this acronym here now, right? So this is the fully fine tuned model that you're going to fine tune every parameters, the bit feed, adapter approach, and LoRa. And this is like counting how many parameters are updated during your fine-tuning process. And you can see the fully fine-tuned one is basically you fine-tune the full parameters. It's going to be large, right? So just hundreds of millions for this case. And when you go to extra large, it's like 1,500 million. Well, for this PEFT method, it's just just update like a very small portion of the parameters during the fine-tuning process, right? So the LoRa is like 0.3 million or for the small one and 0.8 and increase to 4.7 million for the extra large size models. And then they evaluated across variety of different tasks here. So including the natural language inference, sentiment analysis. This is grammar testing, like to see like whether the sentence, the grammar is correct or not. Uh, this is like a Q&As and also some sentiment, textual similarity benchmarks. So basically the score here is the higher the better, right? So basically I think the one key part is we want to compare LoRa to the fully fine-tuned model to see that because LoRa is targets for efficiency. And how about performance? Does it able to match the performance of the fully fine-tuned model? So very interesting observation here is like when it is a small model, like it's just 125 million, LoRa sometimes does not win over the fully fine-tuned model. Because the model is small, you don't have to use path. You just fine-tune the small model, right? That's sufficient. So you see that although it outperforms on some tasks, uh, but there are also some tasks like the fully fine-tuned model still like has an advantage there. But as the model size increases, the LoRa approach seems to be consistently, I would still say comparable. And for some tasks, they is even going to like a plus 1% to the performance on that task. Uh, Regarding to why you use a low rank representation can improve the performance, I guess because it helps with the overfitting. It's just a natural way to avoid overfitting for that task. So maybe it will generalize better, and then the performance may improve, right? If it can handle the uh, generalization better. And comparing to all the other adapter approach, like these different variants of adapters, adding these additional layers, LoRa seems a clear win here. And also it has the benefits of it doesn't incur additional inference time comparing to the adapter approach. So when the LoRa is out, it's becoming really, really popular. And right now, I think it's almost become the standard, one of the standards to how you want to fine tune LLM. So that's the encoder approach, and then they also tested on the decoders, which is a GPT type of models. And again, they also evaluated against on the end-to-end natural language generation challenges. So this challenge mainly is to convert a structured data into a fluent text output. And then they just want to evaluate how fluent the generated text is, whether it is factual, whether it is grammar correct, and then compare it to the actual written text, and to see how it matches with the kind of the human written text there. And then again, it compares the LoRa approach, the medium size, large size GPT-2 with the fully fine-tuned version, and also with other PEFT adapter-based approach. And then the LoRa is like a clear winner of the performance. So basically, it's like with LoRa, there's no point of you fully fine-tune the model, even if you, unless the model is really small, right? Unless the model is really small, then fine-tuning a small model may still play advantage there. But if the model is really large, there's no point of doing the fully fine-tuning. You just use the LoRa, which can help with the overfitting as well to not just benefit the efficiency, but also benefit your model performance. Then they scale it to GPT-3, which is a much larger, like 175 billion. Like they scale it up, right? And you can you can see like how many parameters, like 175 k million. No, this is billion. So 175 billion parameters. And then with the LoRa, you just need. I think this is based on how you want to choose the low rank R, right? So with the smaller R, you will have a smaller set of parameters. With the larger R, you can increase your parameter size. So basically with the LoRa, you just need to fine tune over here is like 37 million parameters. And when you compare the performance, actually it's also comparable or better, actually a lot better, comparing to the fully fine-tuned version. So I think that also indicates that as the scale is up, like as the model scales up, LoRa is going to have more advantage in respect to the model performance there comparing to the fully fine-tuned version. Or maybe also because of fully fine-tuned version over here is really hard to fine-tune, to stabilize, to handle all these many parameters to prevent overfitting and to stabilize the training. Maybe it's like really challenging to get these fully fine-tuned models to reach a good stage, while the LoRa is more straightforward, and you can get a better performance with LoRa easier than just fine-tune the full set. Slide is like which weight matrices in the transformer should we apply LoRa to? So in that paper, they also have just tryouts. Say our budget of trainable parameters is 18 million, and then how we want to distribute these parameters to the LLM, right? One strategy is like we can just apply it to the query matrices, and then we may have a higher rank. Well, we can also apply it to all the query key value output matrices and have a lower rank. I think I haven't seen it. For example, does it uh, basically like how about we just apply it to the top layers, right? In the encoder or decoder, but they haven't done the ablation study over there. But I think definitely we can choose what layers and what specific matrices we want to apply this LoRa modifications. And the result is also interesting. Like they find that with the lower rank, and if you want to update more matrices, especially for the query and values for this case, right? The query and values, it will get sufficient performance comparing to you have a really high rank while you just update one matrices. Okay, and then this is another ablation study, right? So they want to evaluate with the increasing rank, and then apply LoRa to Q or query value or all of the matrices over here, and then what is the performance? And then they observe that a low rank is already very good. Like even when rank is 1, Like even when the rank is 1, it's already getting the very good performance if it is applied to query and value matrices over here, which is quite surprising. Instead of comparing it to you really increase the rank to a really high dimension, but yeah, you won't improve the performance that much, which means that the information is already well captured by rank of 1 or 2 over here. Cool. Let's LoRa. And then I also want to briefly touch about QLoRA. So the QLoRA is kind of another improvement on LoRa. So it's the quantized low rank adaptation. So basically, it applies LoRa to quantized pre-trained model, right? So for the LoRa, it's like the model is usually like a half precision float, 16-bit transformer. And right, QLoRA is basically applies to 4-bit transformer. And they also allows this paging between the GPU and CPU. So it's kind of like, for example, if your computer memory is almost out of memory, maybe the system is going to use some of your disk space, right, to handle the memory outage. Well, it's the GPU can also do the same. So if your GPU memory is almost out of memory for GPU, it's going to do a switch in and out with the CPU memories. So basically, LoRa is also able to do this memory management between GPU and CPU. They also call it like a paging, so that we can train a large model just using one GPU. Of course, that one GPU also needs to be powerful. But it makes it possible to train a large model with one powerful GPU. Uh, and there are several techniques that they propose. One is about the quantization. Usually people, when they do quantization, it's like equals-based quantization. But they find that the weights usually are zero-centered normal distribution, right? Like in the LoRa paper, they also initialize the weights with zero-centered normal weights. So usually the weights is zero-centered, which means that you are going to get more mass in the middle. So the normal float quantization is basically consider the normal distribution, right? Instead of each of the bucket is like an equal weight over here, which may lead to a problem where your middle buckets gets most of the data in, right? But over here, if it's like a normal distribution where you are just going to uh, kind of design the bucket using a quantile method based on the normal distribution you expect. So the one that are away from the center is going to have a larger width, right? And then the bucket in the middle is going to be a smaller width of this smaller range. In the middle, so roughly each bucket will have equal number of data points forcing into that. So basically, this is a more dynamic and like kind of a contact base, and also it can really leverage the each bucket in your quantization rather than just depending on the middle buckets in the previous like equally linear bucket. And then they also apply some double quantizations for more memory and compute efficiency. And uh, and also it allows this model so that they can allow the large model to be trained or run on limited hardware. A naive illustration of this is like, so this is your float example. You can first quantize them into, for example, int4 or int3 over here, right? So it's kind of 0, 1, 3, 5, 7. And then you find that, oh, 2 is not needed or 4 is not needed, right? So basically, you can basically further compress this quantized value into a 2-bit code, like 0, 0, 0, 1, 1, 2. Basically, you skip over 2 if 2 is not needed, and 1, 1, 1, 1. So basically, you can do double quantization to further compress the information into a more compressed format. Yeah, I think the QLoRA is like trying really, really hard. to 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 compress out all the parameter space and memories. And then they also implement the page optimizations, which is what I mean, the page-to-page transfers between the CPU and GPU memories. If the GPU memory is not sufficient, they also allow using some of the CPU RAM, right? And to keep those pages. So if you don't know what is a page, so page in a memory is usually just a memory block. And CPU, GPU is like a 4K to 64K memory block. That's how they manage the information in the memory. And 4K is the most common one. So basically, they will just keep the memory block that is required for the calculation in the GPU memory, and for the ones that is not needed, for now or for the next few steps, they are just going to save that out to the CPU RAM so that they can free up more space for the GPU. They also have a very interesting discoveries. So this is on the 4-bit quantized llama model. And then they first test what is the effectiveness of this quantization approach, of all the 4-bit quantization approach. So this is the float. This is also a 4-bit float, but with the linear equal weight, right? So without the quantize, without the normal distribution considered, they just equally create the buckets. So this is a 4-bit float. And then this is the normal 4-bit float, right? So it's the orange line. And then the green one is the normal float plus the double quantization. It's really additional compression of the parameters. And then it finds that actually from the equal bucket 4-bit float to the normal float, actually it improves the performance a little bit, improves it about like a 1% performance. Well, the normal float plus the double quantization, so double quantization does not hurt the performance. So it's basically the green and the orange actually kind of overlay on each other. So it doesn't hurt the performance much with this additional compression, which is another very interesting findings of how much we can compress of LLM parameters. And then they are going to compare the QLoRA fine-tuning versus the fully fine-tuned models versus the LoRa fine-tuned models. And also they are going to compare with different quantizations, because QLoRA is mainly applies to the quantized model, while the LoRa original paper is mainly for the basically just non-quantized encoder decoder models there. So basically they compare it with the fully fine-tuned model versus the LoRa fine-tuned model versus the QLoRa with different quantization of using 8 bits quantization, or using float 4 quantization, just like a linear equal bucket quantization, or using the normal float quantization plus the double quantization proposed in the QLoRA. And then they find the performance, if you can see over here, I think it's 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 comparable, right? I would not say like it's always better. Some is better. Uh, some is slightly better. Some is like a falling behind, like on this larger model. In this case, over here is like I think all the LoRa approach somehow on these data sets is no better than the fully fine-tuned one on this 11 billion model over here. But at least comparing to the LoRa, I think it's almost equivalent to the LoRa fine-tuning on the original precision, which I mean the 16-bit precision. Yeah, so this is another benchmark on the language understanding accuracy benchmark. And then they again scale it up, right? So they scale it up from 7 billion to 65 billion. And then they compare it with different quantization strategies, like the original precision 16-bit, 4-bit, or the normal aware float 4 and double quantization. And then they find that the performance, again, kind of comparable to the original 16-bit, right? So basically the quantization does not hurt the performance. That's the conclusion. Uh, they they conclude on these MLU datasets. So the from 16-bit to 4-bit plus the double quantization, further compression does not hurt the performance of the yeah on this benchmark.
This has a lot of ramifications or implications for running models on phones and things like that.
Yeah, yeah. Right now on phones, standards is 4-bit. I think because I think I also presented like a 1-bit, right? 1-bit LM. I think right now the on device LM is going to all be the highest will be 4-bit, and maybe they also try the 1-bit LM there. So that is the QLoRA, and I also want to point you to where you can implement the QLoRA fine-tuning. The main functions you need. One is from the bits and bytes config. So this is for the model quantization from the transformer module. So the transformer is kind of the backbone, the major Python module to load and train all kind of Hugging Face transformers there. So, and from the transformer, you can import bits and bytes config. Where you can specify how you want to quantize the Hugging Face transformer model or any transformer model. Because with the Hugging Face, you can just specify the model ID and you can directly download that model for you, right? So it's all integrated together. Well, here you can say you want to load in 4-bit, you want to use the double quantization to true or false, right? And the contact type, this is normal. So N stands for the normal float 4, right? So we have seen that the normal float 4 actually will improve the performance there. Uh, so this is a regional parameter precision. It's a bfloat 16-bit compute type. And then you can load the model by specifying the model ID, right? So you can load your model in, and then I think they are going also to call another function to prepare the model. So basically over here, when you load like from pre-trained model, you're just going to pass in your bits and bytes configurations here, and then that model is going to get quantized. And then you are going to prepare the model for the PEFT, for the LoRa fine-tuning over here. So in the LoRa fine-tuning, you need to specify the rank R. You need to specify which blocks you are going to apply which matrices you are going to apply LoRa. And I think the names may differ depending on what model you use. For this specific model, you can say if you want to query key values, that you want to LoRa fine-tune all 3 matrices, you can specify them here. And another important parameters is the LoRa alpha. So this is so this is so if you remember LoRa structure, right? So it's the regional matrices plus the delta matrices, and alpha is a scaling factor for the delta matrices, right? It can kind of like scale the delta matrices up, and then add it to the original matrices. So this is kind of control of how much magnitude that you want to apply, you want to be the delta matrices added to the original matrices. The larger it means that the fine-tuning effects is stronger, right? And if the LoRa alpha is 0, basically the delta will just go away. There's no delta. There's no parameters of deltas there. So this is just control of how you want your final model looks like. Do you want it to be more like, to trade off between the original pre-trained model capabilities versus the task-specific fine-tuning capabilities? So
Yeah, is that alpha fixed or is it learnable parameter?
this is fixed. Usually people default is 16 or 32.
Okay.
It's a fine-tunable, just hyper parameters, not a parameter,
Yeah.
not a learnable parameter. And then they say you can print out what are the regional all parameters of this model, 20 billion model here, and then what is the trainable parameter model, which is the delta matrices, and then what is the percentage. So basically, you just need to going to fine tune about 0.08% of the original size of the model for your task. If you are interested, yeah, I think all of this is copied from this. You don't need the link. You just search BNB 4-bit training. I can also send over the link in the chat. And this contains all the tutorials of this step of how you can run a QLoRA. How can you fine tune a QLoRA with these packages and settings? To today's meetup. So first we talk about LoRa, right? So you can just remember LoRa as the regional matrices plus the delta matrices, and we are just going to fine tune the delta matrices. QLoRa is mainly focused on the quantization, and remember the 4-bit normal aware, normal distribution aware quantized NF float quantization. So this is a kind of a major contribution of the QLoRA. And also it has this double quantization, and also it manages the CPU and GPU memory pages there. And yet, throughout all these compressions, throughout all these parameters efficiencies, we are still able to match the performance of the fully fine-tuned model. One thing it indicates that to adapt to all these tasks, we don't need that many parameters. We just need the no rank representations to adapt to the task, right? Even though the matrices are huge, and yet the matrices is sparse, which tells that the matrices is sparse, that we actually don't need that many parameters to fine tune to adapt to the new task. Second indicator, it may also mean that fine tune a really, really, really large model is also very challenging. Because like fine tune like 170 billion parameters is no easy task. You need to there can be lots of breaking down like the gradient exploding and all that type of engineering to manage in order to for that fine-tuned model to work. And also given the fine-tuning labels are not that a lot comparing to the pre-training phase, your fine-tuning can easily get overfitted with the original size of parameters. So that's why I think the LoRa and the QLoRa should be the standardized kind of the approach to go when you specifically want to fine-tune a model on a smaller fine-tuned data sets. And if you are interested to know more about the model quantization and also a hands-on session on the fine-tuning with LoRa, so this is the 2 meetups that I have conducted this year. And the recording has all posted under this YouTube channel. And I'm also going to upload today's recording to this YouTube channel so that you can see all the related topic that we have conducted in our previous meetups.